today we are going to start the examples on the Green's theorem and let's first recall the definition of the Green's theorem. So this is, if P and Q are continuously differentiable functions in a simply connected closed region R whose boundary is a curve C, then the line integral of P dx plus Q dy is equal to the double integral over this region R on curl Q by curl X minus curl P by curl Y dx dy. Please remember, if we are having P with dx, then we have to partially derivate P with respect to Y. This is just the way to remember the result. Similarly, if we are having Q with dy, then we have to derivate Q partially with respect to X. Right? So let's move on to the example. Evaluate by Green's theorem this line integral where C is a rectangle with these given vertices. Now it is very important to check what is P and Q. Here it is written that P and Q are continuously differentiable functions. Continuously differentiable functions means the functions whose derivative exists and also those functions are continuous functions, right? And on the left hand side of the result we are having P dx plus Q dy. So we have to take P with dx, right? So here we are having x square minus cos hyperbolic y with dx. So we have to consider this as P. And y plus sin x with dy. So we have to consider this as Q. Very fine. And before applying the Green's theorem, we have to check that whether these P and Q are continuously differentiable or not. Yes, all the trigonometric functions, hyperbolic trigonometric functions, the polynomials, all these are continuous, right? And also their derivative exists. So here P and Q are continuously differentiable functions, right? Let's start with the solution. So this is a line integral given to us, and let this be x and y axis. We have to plot the rectangle first. And the given vertices are 0, 0, pi 0, pi 1 and 0, 1. So marking this as the point 0, 0 and then pi 0. Let this be pi. So this is pi 0 and then is pi 1. So let this point be pi 1 and then 0, 1. So this point be 0, 1. Let's join this rectangle. So this is your curve C, which is a rectangle with these given vertices, right? So let me write this. Let R be the region enclosed by the curve C. That is the rectangle, right? Now since this x square minus cos hyperbolic y and y plus sin x, these are continuously differentiable functions. So since x square minus cos hyperbolic y and y plus sin x, these are continuously differentiable functions. So to apply the Green's theorem, let's take P to be equal to x square minus cos hyperbolic y and taking Q to be equal to y plus sin x, because this thing is with dx. So you have to take P to be x square minus cos hyperbolic y. Okay, now let's apply the Green's theorem over here. So by Green's theorem, writing the given line integral, so this is equal to the double integration over the region R. Okay, this is your P and this is your Q, right? So first term is derivating Q with respect to X minus derivating P with respect to Y, and writing here dx dy. So this is equal to the double integration. Okay, what is Q? It is y plus sin x. So let's partially derivate y plus sin x with respect to x. Partial derivative of P, that is x square minus cos hyperbolic y with respect to y. And writing here dx dy. Okay, what is the limit for x? Yes, it is from 0 to pi. So writing here the limits for x. What is the limit for y? It is from 0 to 1. So writing here from 0 to 1. So the double integration derivating y plus sine x with respect to x. So it is cos of x minus derivating x square minus cos hyperbolic y with respect to y. So first term is 0, derivative of x square with respect to y is 0, minus derivative of cos hyperbolic y is sine hyperbolic y. Dx dy. So this is cos x managing this sign. It becomes positive. So cos x plus sine hyperbolic y. So this is cos x plus sine hyperbolic y. And now let's integrate this with respect to x first. So this is equal to the integration from 0 to 1. Integrating cos x with respect to x gives sin x. Then integrating this with respect to x gives x sine hyperbolic y. Right? So this is plus x sine hyperbolic y and the limits from 0 to pi, and here I am writing dy. Integration from 0 to 1. Okay, putting the upper limit on x we get sine of pi is 0, right? Plus pi sine hyperbolic y minus putting the lower limit we get this term to be 0 plus, and for x also it is 0. Dy. So we are having the integrand now to be pi sine hyperbolic y dy. Taking this pi outside of this integral, so now integrating this with respect to y, we get cos hyperbolic y with limits from 0 to 1. So this is equal to pi into putting the upper limit on y, we get cos hyperbolic 1 is cos. So this is equal to pi into putting the upper limit on y, we get cos hyperbolic 1 minus putting the lower limit on y, we get cos hyperbolic 0, that is 1. So this is the required value for the given line integral. So its value is pi into cos hyperbolic 1 minus 1. Okay, thank you.